Good afternoon, Packaging 450. Welcome to today's lecture. Today, we're on lecture number 9. We're finishing up on chapter 3. We've gone through all of the reading, but it was brought to my attention that some of you all may not have taken Packaging 410 yet, which really consists of a lot of the testing that is in chapter 3. So what I wanted to do is go through a couple of videos to show you demonstrations of what some of these tests look like. So I'm sure some of you all have seen these tests already. Some of you all have actually performed some of these tests, but I think it's really important for you all to see through video what these tests look like so you can kind of match them up to some of the reading, and hopefully that helps. And then I will go through a couple of questions I got about homework. So again, I have office hours. Today's Thursday. I have office hours on Fridays. So if you're available tomorrow for office hours, you have any questions, feel free to jump in. Also, you don't have to stay for the whole office hours. You just come during that hour at any time you're available and just ask whatever question you have. Or if you want to hang out and, see who else jumps on and see if they have a similar question, you could do that as well. So it's just open whenever you want to come in. And then if that doesn't work, you can always email me or set up a time to meet tomorrow if I should be available, fairly flexible tomorrow. So just want to make sure you guys are clear on this. Again, we're going to go through some videos just so you kind of see what some of these tests look like. Brandon, our student that seems to join every day, do you have any comments or questions, or anything that you would like to see a video of, or you think would be a video that would kind of match what we talked about in chapter 3 so far?
Yeah, definitely more so around the testing attributes that go with the automotive and industrial side. So I know, well, I'm not sure actually. Do we do anything with atmospheric conditioning, like the chambers and whatnot for our products?
Well, there is just most of it refers to just making sure that it's at the 70 degrees to 50 degree relative humidity. But, when you run through the test sequences, part of the criteria is to condition it for, so many hours. So I will look that up. I'll do that one first, because that's usually the let's see what we come up with. Okay. So a lot of these videos are very short. Let's see. Okay. This one is short, but you should be able to see.
This is a real B&H customer story. Jack and Barbara, professional wildlife photographers and B&H customers.
Sorry about the ads. I guess I need to subscribe. So this is the chamber, and this is showing what it's set at as far as the atmosphere, and the products that are going to be tested in the packaging will go in these chambers. So for industrial, the products may be a lot bigger, so they just may have a room, and that's where they say the room should be at that, at that temperature and relative humidity. But for most products, consumer products, they can put them in this chamber that is, they can set it to whatever conditions they want. Okay, so that is it for that one. It basically looks like an air fryer, but like I said, for bigger products, the chambers are bigger, or it would just be a room that they can set to a condition of a relative humidity or to a certain temperature. For consumer foods, for example, you can set those chambers to simulate an accelerated test. So you could set it at a, a higher temperature or higher humidity, relative humidity, and that can simulate it being, say, a food. So it could be a food that you want to say, how does this food react or this package perform after 18 months? And there's information and data table you can go to and say, okay, I want to simulate this having been in this, out in a warehouse for 18 months, and you pick the numbers on that table, set that chamber, and then you let it sit in that chamber for however long it's specified in your test protocol to condition it and get it to equilibrium. And then you could take it out and, test it or check it. So that's what those atmospheric conditioning chambers do, and that's what that process is for. Let's see. I wanted to show you a couple of cases. So here's incline impact tester. These are some examples of what they look like. A lot of these are ads for companies selling their incline impact testers. I have noticed more recently on YouTube that most of them are 30 seconds or less, and they're more like ads than demonstrations, but we'll do this one. This one is a minute and a half.
On every vacation at a Verbo home, there's someone like you who reunited the family.
Again, sorry about the ads. So that would be an example. I'm gonna tell you, I'm gonna age myself a little bit, but I've seen impact testing where they have, they used to have chains, and you'll see some of those in some labs. They've had them for a while, they do the job, they're workhorses, and they just run on chains, and they will crank it back to the distance, and then gravity will take hold and run it down. So it simulates, say a truck going downhill, for example. Let's see what else we have here. Any comments or questions, Brandon?
Our impact sled was kind of like that.
Okay.
So so after the drop happens, we would go grab the sled, we'll pull it back, and then we'll like latch it on, and then let the slide come up, and then we'll unlatch it. So ours is kind of gravity fed as well.
Okay. Yeah, so that's more what you see. For automotive, these are much bigger because the parts are bigger. But yeah, the one that you have worked with, Brandon, that one is probably the more common.
Mm-hmm.
So, here's an example. This is a less sophisticated machine, versus this one. I wish you could see a person standing here to get a sense of how big it is, but this is probably about the height of a truck, I'm gonna guess. It's at least 2/3 the height of a truck, because when you look at this rack, you can assume this rack is probably about a 48 by 45 standard automotive footprint. And then this looks like it might be somewhere between the 34 and the 50-inch standard height. So, and that's the ceiling. So I'm gonna think that this is probably simulating the back of a trailer. So just so you can get an idea, this is probably about 50 inches high. And if you stack them too high, it would be about 100 and fill up the trailer from top to bottom. So just to get an idea of how big some of these items are, but I want you to see that for the incline impact, just to get an idea of what it looks like. Okay, next we have some vibration tests. Let's see. So probably what I should have done was just save these, but I saw so many of them when I typed it. Okay, so one of the things I wanted to show you is for the vibration test, right? Okay, so yesterday we talked about how they will test a vehicle for noise. And one of the things that distinguishes a regular vehicle from a luxury vehicle is that it can dampen sound, or you don't hear as much noise. So that's why shaking a vehicle or even a part of a vehicle is important. But it's the exact same test basically that you're running for the packaging. So this is an example of a seat, an automotive seat being vibrated.
Good morning. My name is Nigel Plummer from Data Technologies. We're a high-tech Israeli R&D company.
And you can see that this seat is this vibration table is basically, it's a vibration table, and it's moving this seat in 6 different axes. So, or 3 different axes, 6 different movements. So you can see they can do it on the side, because what they're trying to simulate is the sway, the heave, all the roll, all those different movements. So now it looks more like a traditional vibration table because they put the platform on. And looking at this video, it looks like the car moving on a bumpy road. So where they're looking for squeaks and rattles, we're looking for damage to the parts in a pack shipping to the assembly plant, whether it's an OEM or whether it's a tier 2 to a tier 1, wherever it's shipping to. We're looking for those parts. Are they packaged in such a way that if they're class A, are they going to vibrate and scratch each other? Is the surface going to be scratched? Or you see they're bouncing up and down for that. Is there going to be so much bounce in the trailer that if it's an electronic part, is that electronic part going to hit resonance frequency, or will it break some of the solders and welds? Those are some of the sort of things that we're trying to simulate. And you see they can even bounce it up and down while it's turning, which is going to imitate a car or truck turning or maneuvering, switching lanes on a road. And then this is even simulates braking. So this would be, they're showing the car braking, but you want to see, you know, if the parts on a truck in the pack, if the truck brakes, what does that look like? You know, what sort of shock events are you going to see? And the shock events would be impacts, damage, you know, potential for any issues. Here's another one with it's going up and down and turning at the same time. So it will be basically changing lanes, moving maybe around potholes and those sorts of things. So you can see this is an even bigger one, a bigger platform. So now again, it looks like a traditional table for vibration that we're used to seeing in packaging. So this one, you know, they even have a temperature chamber available. So when I talked about the conditioning, you know, you could actually put your parts, large parts in a chamber like this for whatever period of time is deemed in your requirements for the test to condition it ahead of time. And then you can run that test in that same area or that same room that's conditioned to the specified amount, which would be that 72 degrees and 50% relative humidity. So you're not going to see this in most facilities, test labs. Mostly you're going to see the regular vibration tables that just do, you know, one dimension versus moving in 6 degrees of motion. But some of the larger test labs for large automotive parts and vehicles, you will see that. Okay, I think that's it.
Now's the time to get a 2022.
Okay. I would like to show you a couple more. So I think the vibration, you know, they talked a lot about the vibration. Not a fan of the disco video music, sorry. So this is a seat. These are some of the tests that are done in seating, but you know, they're imitating movement in a vehicle, wear and tear, which we're not really interested in, wear and tear of the parts. But when they start doing the testing for the vehicle moving, you know, that's really simulating the transportation testing. And again, they're showing the characteristics of these seats. This is important to know. So here's vibration, which is what we're looking at for packaging. It's important to understand the performance of the vehicles during a lot of this durability testing, because then it helps you design a pack. Because then you can understand, you know, what's important. So for this is showing, you know, this is simulating a person sitting on the seat, and then are they rubbing against it? You know, this is environmental, another environmental chamber. You see it's much bigger. So when I worked for a seating company, they had a similar test area for the seats, but we could also run packaging items if we needed to. because for automotive seating, they have pallets that they use for the finished seats. And then the finished seats go on these pallets, and they have to do testing for all that as well. The thing that is interesting, at least to me, about the seat packaging is that seats use a lot of the same materials that we use for packaging. So they use the foam, the fabricated foam, which we use a lot for our parts. For example, this is an example of a fabricated foam tray that's holding parts. And they use that same type of foam. That would be, it's pink because it's for electronics, but they use the same type of foam, same exact type of foam for some of the seats that we use for packaging. Let's see. This one's what is a vibration shaker? So apologize for the ads ahead of time.
Brilliant trick to cool your home in 90 seconds. Tired of hot and
In order to vibration test your sample or device, we require a source of vibratory energy. Vibration labs use two principal types of machines to provide this energy: electrodynamic or electrohydraulic shakers. Each type of shaker has its advantages. Electrodynamic shakers are capable of a wide frequency range from 5 Hz to 3,500 Hz and displacements up to 75 millimeters. Electrohydraulic shakers are typically more rugged than electrodynamic shakers and are capable of larger displacements, but are generally limited to frequencies below 200 Hz. We use electrodynamic shakers at Paragon Systems Testing to perform vibration testing in 3 axes. An electrodynamic shaker consists of 4 basic components: an amplifier, an actuator, a controller, and a slip table. The shaker amplifier works very much like a stereo system audio amplifier. It uses mains electrical energy and takes a low-level alternating electrical signal from a vibration controller and amplifies it into a signal of many thousands of watts. If we continue with the stereo system analogy, an electrodynamic actuator is similar to an audio speaker. In a stereo system speaker, the amplifier alternating electrical output is applied to a coil of wire suspended in a circular gap surrounded by a permanent magnet. The coil in the speaker is forced to move back and forth due to magnetic induction. The coil is attached to the speaker cone, which makes sound by moving the air in front of the speaker cone. In a vibration system actuator, the amplifier output is also applied to a coil. Except for very small shakers, this coil will be surrounded by an electromagnet instead of a permanent magnet. The coil in an actuator is forced to move back and forth by the same principle as in an audio speaker. In the case of a shaker, the coil is attached to a mounting surface for vertical or Z-axis testing and is called the armature. The armature and its attached coil, the electromagnet, and the surrounding support structures are called the actuator and are visible here in a partially disassembled actuator. The amplifier input in an audio system can come from a radio receiver or a digital media player. Your ear senses the level of sound produced by the speaker, and you control the level of that sound by varying the volume control on the audio amplifier. In a shaker, we control the actuator output levels a little differently. The shaker amplifier input is provided by a vibration controller, which is programmed to produce specific acceleration, displacement, and frequency test profiles, which match the vibration test method. An accelerometer sensor mounted to the armature measures its movements. The controller senses this accelerometer signal and adjusts the amplifier input so that the armature movement corresponds with the vibration test profile programmed into the controller. The actuator by itself can only produce vibration in one direction, typically in the vertical or Z-axis. Vibration tests usually require vibration to be applied to a test article sequentially in 3 mutually perpendicular directions: X, Y, and Z. In a shaker, this is typically accomplished by rotating the vertically aligned actuator 90 degrees to a horizontal position after completion of the Z-axis test. The now horizontal armature is then attached to a horizontal sliding surface. This sliding surface is called the slip table. The slip table surface is where test articles are attached when performing X and Y axis tests. You can learn more about the individual components of an electrodynamic vibration shaker by following the links below.
Okay, so I think that one was a pretty good one. There are a couple other ones. I'm not sure which ones to show you, but I just want to make sure that you have a good idea. Let's see, there's vibration testing. We'll try. We'll do this intro.
Hyundai Santa Fe versus Subaru Outback. Hyundai Santa Fe.
And then I will also do one for drop testing.
Okay, everybody, we're going to go ahead and get started here. So today is going to be all about vibration and shock testing. We're going to go into some guidelines of testing, as well as control strategies and fixturing as well. For those of you that don't know me, my name is TC Beinke, and I'm the National Account Manager for the testing division here at J.A. King. So to start off, what is vibration? Vibration is defined as periodic motion of a rigid or elastic body about an equilibrium point.
And I wanted to mention too that this information is not going to be on the homework, but I think it will help you with the homework, especially for anyone that has not taken packaging 410 yet.
And when we're talking about vibration testing, specifically that body that experiences the vibration, we refer to as the DUT, or the device under test. And typically with vibration testing, we're going to be testing under one of the 3 mutually perpendicular axes, X, Y, or Z. So why do we perform vibration testing? The main reason we do this is to simulate stress from real-world vibration scenarios. This could be vibration from an automobile going down the road, experiencing rough terrain. That's a good example of real-world vibration scenario. And I put some images here showing some other examples as well. We could be talking about vibration from machine operation, vibration from locomotives, or even vibration from aerospace components, and even wind itself can cause vibration as well.
So for this one, the 2 that we've mainly talked about are going to be the train and the potholes. Those are two examples of what we're trying to simulate.
So I also want to go into just some basic vocabulary about the actual shaker system itself. So you'll see here, I've pointed out a shaker in both the vertical and horizontal orientations. The armature is the moving member of the shaker, and this is what's actually going to transmit vibration into your fixture and DUT. The armature is going to be bolted to, a lot of times, either your head expander or your slip table, whether you're in the vertical or horizontal orientation. And the point of the head expander and slip table are both essentially just to give you a larger working area to bolt your fixture or DUT to for vibration testing. So there's a few different types of profiles, both for vibration and shock. For our purposes today, we're going to stick with the ones that are most common that we run into most of the time. For vibration, this is sinusoidal and random vibration testing. And for shock, we're going to be talking about just classic shock testing. So let's go ahead and start off with sinusoidal or sine vibration testing. This is the simplest form of vibration, and the easiest way to think of sine vibration is to consider a mass and spring system. This mass, as it's supported by the spring, is going to operate along a sine curve. And you see here that I've put in a figure of your basic sine curve and pointed out some of the key parameters here. You'll see all the way on the right side, I've pointed out the displacement, which is essentially just the distance from the x-axis and the peak of that sine curve. A lot of times when we're talking about vibration, sine vibration testing, we actually refer to the peak-to-peak amplitude, which is just double the amplitude itself.
So basically what he's doing is going over, if you were to graph this movement on a chart, this is what the movement would look like. The vibration comes in waves, and this is how it would look graphed out.
Also, I want to point out the period, which you can see there on the left side of the figure. We're also going to talk about frequency a lot as we go forward. And the frequency is just 1 over the period or the reciprocal of the period. I also want to point out that this would be an example of a sine dwell. So you can see here that all the parameters in this case are staying constant. Your displacement, your frequency, and your acceleration are staying constant as time goes on, and nothing's changing. We're going to talk about a sine sweep in a little bit here, and you'll see that that's not the case. We will have some parameters changing during a sine sweep. So why do we use sine vibration? Main reason we use sine testing is to find a resonant frequency. So a natural frequency of a system is the frequency at which that system oscillates when it's not subjected to a continuous or repeated external force. So it's the frequency that that system is going to oscillate at when it doesn't have any external vibration applied. And resonance is what occurs when the applied frequency equals the natural frequency. And the result of that is an exponential increase in the amplitude of vibration.
So basically what he's saying is when you're in a lab and they're running a test for resonance frequency, what they're trying to do is they're trying to determine what the natural frequencies are of, let's say this is speaker. And inside of the speaker, there may be something that has a resonance frequency that a natural frequency that is similar to a frequency of a truck vibration, for example. And when those two meet, it amplifies that. So instead of it shaking like this, that part inside of the stereo that has that natural frequency, when it's on a truck and that truck, instead of just moving at that same frequency, what it does is it actually makes it increase. So that can cause it to, shake and cause a lot of damage. And that's what this is graphed out on this chart. This would be, this might be the natural frequency. It seems really low, but when that truck, if it's on a truck and it hits that same frequency and it just amplifies this, all of a sudden you see this big event, you see this big bump in the amplitude, meaning that part whatever that natural frequency is, if it matches the truck, it will, it will amplify. And that is an opportunity to damage a part. So before testing, sometimes you'll see test labs check a part for the resonance frequency, and that's what they're checking for. They want to see, is it going to vibrate so much and it's going to amplify it, and is it going to cause a lot of damage?
So if you take a look at the figure I've put here at the bottom, this is a good example of what hitting a resonant frequency would look like graphically. You can see as the frequency increases and you do hit that resonant frequency, right at about 175 hertz, you get a huge spike in your vibration amplitude. So looking at this graph, you would know that the system you're testing has a resonant frequency of about 175 hertz. So usually when you're doing sine vibration, you're going to perform a sine sweep. That sine sweep is used to find resonance in either your DUT itself or the fixture.
So that this chart is showing what they do. They'll imitate, say the truck is running, vibrating at this frequency and it's vibrating this much. You can see the different types of vibration and it changes. And eventually, if let's say the part has a, resonance frequency at, 5 Gs or something like that, it will bounce up on the chart, and like that last chart that he showed you. And then you'll know, okay, this is where this particular part is vulnerable. But we'll let him talk.
And you want to find resonance in the DUT. Usually the reason that you want to do this is to see what kind of damage you're going to experience at that resonant frequency. So usually you would do a sine sweep over a specific frequency range. And once you find that resonance, you would perform a dwell on it to see what kind of damage your DUT is going to experience. The other case would be doing a sweep for fixture validation. And the reason that's important is you want to make sure that the resonant frequency of your fixture does not fall within the frequency range of the actual test that you want to use that fixture for. And if you look down here at the bottom, this is just an example of time domain data of a sine sweep. And you can see as time goes on, that frequency is increasing.
So he mentioned the dwell. The dwell is you want to run it at that frequency that you know is going to amplify that to see how long does it take to damage it. If it bumps up once, it may not be a big deal, but if you amplify for a long period of time, how long will it take to damage it? The second thing he mentioned was about the fixture. So if you have a fixture on your vibration table and that fixture has a resonance frequency that you're going to vibrate your pack at, now that fixture is going to be moving more than normal, and it could actually cause more damage. So you want to make sure that your fixture, whatever's holding your package or part down on the vibration table, isn't shaking unreasonably. Sorry about that.
Good morning. My name is Dan Ambray. My company.
Didn't mean to do that.
That's too fast or the displacements are too small.
This is what happens when an old person gets a hold of YouTube.
We have fun.
So there's a few different types of, let's go ahead and start off with the spring is going to operate double the amplitude itself.
I don't want you to sit through this again.
So looking at this graph, you would know that at resonance, you would perform a dwell on it to see what kind of damage your DUT is going to experience. The other case would be doing a sweep for fixture validation. And the reason that's important is you want to make sure that the resonant frequency of your fixture does not fall within the frequency range of the actual test that you want to use that fixture for. And if you look down here at the bottom, this is just an example of time domain data of a sine sweep. And you can see as time goes on, that frequency is increasing. So this is an example of what a sine sweep would look like on your actual vibration controller. In this case, and in a lot of cases with sine sweeps, you're going to start out with a increasing acceleration and a constant displacement until you reach your target acceleration. In this case, it's 1g. Once you reach that target acceleration, you're going to continue at 1g all the way up through your frequency range and then back down. I also want to point out the axes on this graph. You can see both the x and y axis are logarithmic. The reason this is so important is because it's going to enlarge small acceleration contributions. This is going to help them actually show up on the graph so you can see them. You can be sure that you don't miss any spikes in acceleration that way. Also, I want to point out that the x-axis here is frequency and it is proportional to time. So if you were to perform a sine sweep, you'd actually be able to see your shaker operating along that curve, and it would track along that green profile line from the left side of the screen up and to the right side of the screen to the higher frequency range. You'll see in a minute here when we go into random vibration, that's not the case. The x-axis is actually not proportional to time. And we'll talk about that a little bit once we get there. So random vibration oftentimes is used to simulate some sort of real world vibration scenario, whether it be transportation or machine operation, any of those real world vibration scenarios that we talked about a little bit at the beginning of this presentation. That's what you would use random vibration for. It's much more realistic than sinusoidal vibration, and that's because in the real world, the future of vibration is not predictable. So you need something much more random and sporadic to actually accurately simulate it. And you can see down at the bottom, I have put a figure of time domain data for random testing, and you can see it's very sporadic, especially when you compare it to a sine graph. Now for sine testing, the intensity is dictated by your G level or your actual acceleration. For random vibration, it's a little bit different, and the intensity is actually dictated by the GRMS. And that's essentially a measure of the cumulative energy input or a measure of how hard your shaker is really working. So to give you a better idea of what really is the GRMS, it's calculated just as the square root of the area under the profile curve. So you can see here, this is what a random vibration profile would look like on your actual shaker controller. And the square root of the area under that green curve, that's going to be your GRMS. Now, it is important to note also that while this GRMS does indicate your test intensity, two different curves with the same GRMS are not necessarily equivalent. They could have completely different shapes and different frequency ranges as well. So I want to talk a little bit about the X and Y axis for random as well. As I mentioned earlier, the X axis here is not going to be proportional to time. So rather than tracking along that green profile curve like we did with sine testing, with random vibration, at any point in time, your shaker could be operating at any point along that green curve. So it'll actually kind of bounce around that curve as you're performing testing. Also, I want to point out the y-axis. You can see for sine testing, it was just g's, it was just your acceleration. And in random vibration testing, we've got g squared per hertz. These units kind of confuse people sometimes, but essentially, when you take your acceleration, square it, and divide it by the frequency, you're essentially just normalizing those values. And this is important here because the acceleration during random vibration testing actually depends upon the bandwidth that you measure that acceleration. So before you...
So he's basically just talking about graphing out the movement on the vibration table. As that's what if you graph out that movement, that's what it's going to look like. And he was talking about the difference between the two different types of vibration sequences that you run and what it looks like if you graph it out.
Perform a test, the profile itself needs to be defined. And for random vibration, there's a few different ways of doing that, both graphically and by using a breakpoint table. And I've shown both examples here. You can see on the left, that would be an example of graphic representation of a random vibration profile. And it kind of speaks for itself. It gives a graphical representation of the actual shape of the curve itself. It gives you some key frequencies and accelerations. And then in this case, they actually gave you some slopes as well. And a breakpoint table, on the other hand, rather than giving you a graphical representation, it just gives you every single key frequency point and its corresponding G squared per hertz. So when you look at vibration specifications and procedures, you'll see either a mixture of this or one or the other. So now I want to move on to mechanical shock testing. Shock testing is essentially used to simulate either impact, drops, or some sort of explosive force. The reason shock testing is so important is that shock excites all resonances.
So for packaging and transportation testing, we're basically interested in impacts and drops. So hopefully no explosions. That would be a totally different issue. But we're basically talking impacts and drops.
We've already talked about how important it is to test at resonant frequencies because you're going to get that increase in amplitude. And when you perform shock testing, each component of what you're testing is actually going to quiver at its own natural frequency. You can see here I've included a figure of a half sine pulse, and I pointed out some of the key parameters here. You can see there's the amplitude pointed out there at the top of the curve, which is the acceleration level. And then I've also pointed out the pulse width, which is another key parameter. And that pulse width is essentially just the actual duration of the test itself. So you've already seen one example of a half sine pulse. And as I mentioned, this is the most common pulse shape. On the right there, you can see what that pulse would look like in an actual vibration controller. But there are other pulse shapes as well, other than just half sine, such as sawtooth, rectangular, and trapezoidal. And the trapezoidal shape, the sawtooth shape is what you can see there at the bottom of the screen. As I mentioned, half sine is the most common, but these days specifications are actually moving more towards sawtooth, and that's because there's a more realistic residual spectrum for sawtooth pulse shapes.
So, well, the half sine gets used as easy, you know, people have been programming it, but they're finding it some of the other shapes or types of amount of movement and the time that it moves, the amount of vibration and the time of that vibration is more realistic with the other profiles.
Now, I also want to talk about the importance of including a climatic element in your vibration or your shock test. This can be especially useful for transportation tests. So if you think about having your part in the back of a truck, it's going to be bouncing around, it's going to experience vibration, it's going to experience possibly some shock, but it's also going to have some environmental conditions that are changing during this as well. So by including a climatic element in your test, it's going to help to more closely simulate that real world environment.
I like the way he said that in about 5 seconds. I think I spent about 10 minutes saying that yesterday, but he summed it up really well.
And this is also really important because temperature and humidity can affect the actual material properties of your part. So if you're testing at a higher temperature, the material is going to be more rigid, more ductile. If you're testing at a lower temperature, the material is going to be a bit more rigid. And
that was where I talked about Minnesota in the winter versus Florida in the summer. What he's saying.
It definitely affect the results of your test. This is just an example of our setup at our Greenville, South Carolina testing facility. You can see we've got our shaker there, and right behind it is our environmental chamber. So we can actually slide the entire vibration system into the climatic chamber, seal it up, and perform vibration testing with the climatic element as well.
So down in South Carolina, they are doing, because it's in that southern automotive corridor, they're doing a lot of automotive testing. So they have setups large enough to do larger parts, even small vehicles, depending on what it is, and they can condition the room and condition the parts and then test them all at the same time instead of having that little chamber that looks like an air fryer.
The climatic aging or temperature cycling as well. So I also just want to list a few common specifications that we run into a lot for both vibration and shock testing. For transportation, you'll see I've pointed out a couple different ASTM specifications. Both of these we run into quite a bit, and they're both very useful because they give different profiles based on the method of transportation, whether it be air, ship, or truck transportation. Also, I've pointed out a couple of automotive specifications for vibration testing.
Now, those automotive specs that he's listing, those are not automotive packaging specs. That's not the AIAG RC9. You notice that's not here. He's talking about testing automotive parts, like that video where I show where they were vibrating and testing the seats. So that's the difference between the automotive versus the transportation.
That ISO specification is very useful. It's actually geared more towards automotive electronics, but it's oftentimes used for all types of automotive components other than electronic components. I also pointed out an IEC specification. It's a great spec. It provides a lot of good guidelines for vibration testing, but it's important to note that it's more of a guideline specification rather than providing actual test parameters. So the IEC specification, as well as that military standard that I've posted there, the MIL standard 810G, both of those specs are going to require some tailoring on your end. And then, of course, OEMs tend to have their own specs for vibration as well. And oftentimes they'll actually reference back to one of these other specifications that I've already listed. So now, how do we actually measure and control our acceleration during testing? The way we do that is with accelerometers. And the most common type of accelerometer, the one that we tend to use all the time, is piezoelectric accelerometers. And you can see I've put a figure here showing the basic makeup of how these accelerometers work. And essentially, it's just a mass and spring system, with the spring actually being a crystal. And as that crystal compresses or elongates, it's going to generate an electrical charge, which is then converted back to acceleration by your vibration controller. And the reason we like to use these piezoelectric accelerometers is because they've got very high resonant frequencies. And this is really helpful because it means you can use these accelerometers for a wide range of vibration tests. One of the main downsides to these is that they cannot measure very accurately at low frequencies. So pretty much anything below 5 hertz, they're not going to be very accurate. Luckily, most vibration tests are going to be above that level. If you do want to measure and test below 5 hertz, you can use a capacitive accelerometer. There are some downsides to those accelerometers though too. For instance, they're not great at the higher ranges. So like I said, we tend to stick with piezoelectric accelerometers, but you really have to choose your accelerometer based on the actual test that you're performing.
And this is something that the test labs have already worked out. So if you're running some packaging testing, transportation testing for your parts, and you're using a standard ASTM D4169 or an RC9, one of the ones listed in the AIAG spec or guideline, any of those specs, you go to any lab that's going to run any of those test sequences, they've already worked this out. This is just an FYI.
Now, accelerometers are only as good as where you place them. So you really want to make sure that you're controlling your acceleration as close as possible to your input vibration location. So you want to place it on the fixture itself, not directly on the table, and you want to have it near a mounting location and on a rigid member.
So again, FYI, if you're in a test lab, the test lab staff has already worked this out and they know this already, but good for you to know. If you see someone put an accelerometer right on top of your product that you're testing, that might be a red flag for you to talk to them. But generally they're gonna have all this stuff worked out and they understand this already.
One exception of this is, for instance, if you're performing transportation testing. For these tests, a lot of times there actually is no fixture. You're just placing the DUT directly on the table and letting it move about freely during testing. So in this case scenario, you actually would place your accelerometer directly on the table itself for control.
And many times you're looking at transportation testing, you might be testing a pallet of something. So it's a lot heavier. You don't necessarily need a fixture to hold it down unless you're testing something individually. But for transportation testing, you're probably testing a whole pallet, how that pallet performs on a truck or on the rail car.
Now, speaking of accelerometers and controlling vibration with them, there's a few different control strategies that can be used. Essentially, you can either control with one accelerometer or with multiple accelerometers.
And I'm going to go past this because generally, we're trying to simulate what's going on. So accelerometers are capturing what might happen.
Test. What you could do is you could place multiple under test, and if you're using minimum control strategy.
So for automotive or just for transportation testing in general, when you see accelerometers, it's generally going to be like on a truck or something, not in the test lab.
Because it does help to minimize the effect to either the armature or the head. So since we did mention fixturing, let's go into that a little bit. A fixture is really just anything that couples your DUT to either the armature or the head expander or the slip table. Fixtures can be extremely complicated, or they can be as simple as just using clamps. Now, the first question you're going to want to ask yourself when you're designing a fixture is, what type of material should you use? A lot of people think that the best route to go is to use steel because it's rigid and it's strong, but this is actually not the case for vibration testing for a few reasons. Steel is very heavy. When you're performing a vibration or shock test, you're going to want to keep your weight as low as possible. And also, steel has really poor damping characteristics. So if you think of hitting a steel object with a golf club, you're going to have that feedback back through the club and into your hands. And steel actually performs very similarly during vibration testing. It's going to ring. So if you do have to use steel, you're going to want to make sure you use it only at very low frequencies and for vibration profiles that are not very aggressive. So what you're going to want to use instead is materials that are lighter and that have better damping characteristics. And the go-to for that is either magnesium or aluminum. Magnesium is probably the best option. Now, the next question that you're going to, and
I don't think we necessarily need to
Actually,
know this as well. These are things that, this is probably, he's talking to people that are looking at either buying this equipment or they work in labs that use the equipment. I more want to focus on how the vibration works versus how they're actually, running the testing. So
an easy way. Careful when you use clamping.
You can always go back and look at the entire video. You can look it up on YouTube. This is just talking about the capabilities of the equipment. Your test lab, if they can run the test and they know what your product weights are, you're going to generally have a lab that has the capabilities of what you need. So labs that run like ISTA testing for air shipments, most likely most of those products are going to be lightweight. But for a company or lab that runs testing for automotive parts, say if they do a lot of rack testing, their vibration tables are going to be rated to vibrate heavier products.
Create a fixture that's going to. So that's all I've got for you guys today. I'd like to go ahead and open it up for questions now. If you've got questions, you can, as I mentioned at the beginning of this, you can type them directly into the chat, or if you want them to be anonymous, you can send them to Lisa Messenger directly. Lisa, do we have any questions?
I have a couple for you.
Okay.
Someone wants to know, what is the max payload of your shaker?
That, like I said, that would already be worked out from your lab. If you're looking for a lab that's testing racks for engines versus a lab that's testing vibration testing for CD headrests, CD players and headrests, the tables will be different.
DUT and fixture combination
Okay, I'm just gonna
that you want to
stop this.
run is
And I think that gave a pretty good example of how the vibration tables work. Let's see whether or not we get some actual, let's just do drop tests instead of automotive, because we're getting drop testing for, okay, I think this one's, well, that's a short one. I just want you to see what drop testing looks like. I'm going to guess most of you have seen this already, because being at Michigan State, you probably have seen it, but a lot of people like to drop iPhones. Okay, we're gonna look at this one really quickly. So it looks really boring, but it does provide a lot of information. Let's see. This one is an Amazon one, so. So that is one of the newer test standards that Amazon is using.
Fred Smith here.
And now we missed the, moved into the ads. Okay, so I was just trying to see if there's anything else that might be a good one for you to see for drop testing. So you can see a lot of these are ads for the equipment, but they actually give you a good idea of what they look like. I think that first one showed you, okay, so this one's dropping a bottle, but you can see these boxes that they're turning them at different angles. And that's because you want to get the edges, the corners. I put this is a little bit better. You want to get, you know, the edges, you want to get corners of these drops. So you'll notice when they orient, the drop tester can hold it. See how it's holding it, and it can hold it in the position. So you're getting your impact in a specific spot. So that's what the drop testing is. There was one video that I wanted to show you all that came from the Automotive Packaging Summit. Let me find it here. Okay, so I've met him before, and he actually runs a lab at Clemson. Sorry about that, but they do a lot of automotive testing there.
A real pleasure for me, an honor for me to get to share some of what I do, a little piece of my world with you. I love my job. I love what I get to do, and I enjoy getting to talk about it.
And he's really this excited all the time.
First, I wanted to say a couple things. This is my third, I think it is the third Auto Pack. And it's been a real joy for me to see this grow and to mature over the years into a real high quality event. I think that it fills a niche in our environment, evidenced by all of you being here this morning for what looks like a real full day of excellent content. But I want to encourage you to not miss the fact that intentionally in the schedule, as I was looking through it, in addition to some great content, are some real opportunities to network with one another. And if you're like me, your emails are building up and you're maybe getting vibrated because your messages are lighting up. I encourage you to use this time to get to know one another. That is probably the single most valuable aspect of some of these events that I go to on a yearly basis, is the opportunity to network. Automotive, packaging is a huge industry. Automotive is a huge industry. Automotive packaging is a huge industry, but we're really kind of a small group, aren't we? And we see a lot of the faces again and again at these kind of events, like last night. And it was a real pleasure for me. I think last night at the reception was.
Let's get past this a little bit.
So it was great to see you guys last night. What I want to do is take the next 30 minutes or so and give you an overview of distribution package testing, okay? This is, for some of you, this is going to be an area that you're well familiar with. And I hope for you in this presentation that there'll be a couple nuggets that you can take away from this. For others of you, this might be brand new, in which case what I hope I'm able to demonstrate this morning is the value you can bring to your organization by incorporating package testing into your packaging development, even into your product development. If we can push that back so far as to move it into the product development stage as well, then the value that can bring to your company. So we're going to give an overview of what package testing looks like, some of the organizations that publish standards, and what's available to you for package testing. But before I do, I want to talk a little bit where I'm coming from. It kind of informs my approach. And connection with.
Skip past this a little bit, but you can look him up, Dr. Greg Batt. A lot of his products are automotive that he tests at the test lab at Clemson.
Packaged products, and so we're going to talk about that a little bit today. Like James, we've got a facility at Clemson that I serve as director of, that provides, in addition to meeting the needs of our undergraduate students and our graduate students, we also provide for industry in the way of testing services. And we're happy to talk on the phone and work with you to develop test protocols, to provide those testing services, material evaluation, and even some consulting services. So this is us, and I really want to start with why do this? Why test? Can I just put my packaged product in the back of the truck and send it from point A to point B and open the truck up and take a look and see what happened inside?
Talked about this yesterday.
Why do I need to go into a laboratory and conduct this kind of testing? And first of all, I'd say that's a great idea to actually do the field evaluation. But what I want to do is give you some reasons why we want to bring this into the lab, and it affords us the ability to get a closer look at what's going on, because Maybe that truck driver was having a good day. Okay, maybe he took a nice route from point A to point B. Maybe the mechanical handling of that. Everybody was in a good mood. It was Thursday afternoon, Friday afternoon. Everybody's happy. But what if it wasn't? You don't know what you're getting when we do these field trials. So when we come into a laboratory, we have the ability to control the environment. Okay, we can isolate down to a particular hazard, not just what happened between point A and point B, but we were able to isolate down, this is a shock issue. This is a vibration issue. We're having an issue with compression forces. And we don't need to worry about these other here. Let's focus our attention there. So we have the ability to control the environment. We have the ability to create repeatable tests. Why is that important? If I'm making financial decisions between packaging A, packaging B, and packaging C, I need to test all three of those the exact same way, don't I? In a side-by-side comparison with a test that's repeatable. There's something valuable about watching your packaged products pass or fail these tests. One of my
That's a good point. He
encouragements to
mentioned if you
later
have
in this
multiple
presentation
types
is
of,
to be there if you can.
if you have multiple types of packaging that you're still early on trying to determine which one is best, running a lab test is a really good way to compare apples to apples.
To hear, to see what happens when things go wrong. We can learn a lot by just being there and watching things fail. We don't get the opportunity to do this in the back of the truck. Accelerated testing. This is particularly applicable to vibration. We'll talk a little bit more in depth about this, but the ability to take a 10-hour truck ride and simulate the damage potential of that in 3 hours. Well, now I can do 2 of those tests in a day.
And that's where you see in your reading where it talked about having, you see your plots and they take out this portion where there's no activity and you're only using the events that were shock events in the lab. That's what he's talking about.
And I can maybe shorten my development process. And then lastly, we get immediate feedback. Okay, we can go into the lab and we can make modifications. We can try different configurations and then go and immediately retest. And again, an opportunity to shorten that development time. Okay, so when we look at performance testing, there's really three ways that you'll see these tests broken down. The 3 levels of testing, if you will. The first is a very basic level of testing called an integrity test. This is really great for comparing A to B to C. These are typically pretty intense tests, intense vibration, intense shocks, for the purpose of, and what we would like in a test like this is to see some level of damage so that we're able to differentiate between our different packaging options. Or maybe our distribution environment is so complex and we have so many different options on the way things could be handled that we don't have any data specific to one lane or one distribution.
So this is what we talked about when you have the, maybe you're just shipping something on a truck on a milk run, a very short distance, maybe 5 miles or across the street or 50 miles versus something's coming from overseas, getting put on a barge, put on a truck, put on rough roads, put on a boat, put in a rail car, flown, all these different options. He's referring to that
cycle that we could use to simulate. So we're just going to use a very basic test at a high intensity level just to see how those types of inputs that do exist in the environment could potentially affect our packaged product. So that's kind of base level testing. Very simple, inexpensive to do. The next level up, you see the word simulation come in here, general simulation. We are actually simulating what happens in a particular distribution environment. So we're making choices like we have an air ride truck. We're making choices like this is how many miles we expect to drive. We make decisions based on, we know how many high we're going to stack these in a warehouse. So this is a next level of complexity. It adds a level of complexity to our testing.
So this is when you know some of the parameters of your testing. The first one was worst case scenario. These are all my different opportunities that there could be damage. The next one is I know some of the parameters of where it will be stored, how it will be shipped, and I want to look for damage in the known scenarios?
It takes longer for us to do these tests. There's often some environmental conditioning that occurs that we incorporate into this level of testing. That's kind of our level 2 testing. What we're beginning to see in working with companies, both automotive, and there are lots of examples of this outside of automotive, are companies taking a focused simulation approach. Using some generic profiles and some generic tools to predict compressive loads is not enough. They want to see what's going on in their particular environment. Most of us in this room are carrying a data recorder of some form, right? Maybe in our watch, maybe definitely in our phone. With the proliferation of data recorders and the opportunity to collect our own data, I see companies, and we're working with companies who are instrumenting their trucks, their drivers. They're looking at their mechanical handling and measuring, analyzing, and then using that data to inform their test standard. Okay,
so what could be happening with this? It's what this might be driven by is having certain, maybe you have 3 production plants that make parts going to your customer, and you're getting damage from one of those plants and can't figure out why. And if you're able to track or, collect data from a particular route, you can see, is it happening on the route? As an example, this would be an example of trying to figure out where the damage is coming from.
We have company-specific test standards, very popular one of these, and fortunately, you guys don't sell, to my knowledge, you're not selling automotive products directly on Amazon, but that's a big one right now. I just came from a conference last week in Chicago focused on this e-commerce and all the changes that's bringing about for package testing. Some organizations that publish these standards come out, and you'll recognize many in this list. I'm going to focus on the first 2 because I think these organizations, the International Safe Transit Association, ASTM, is particularly here in the U.S., are 2 dominant standard writing organizations that are doing work in advancing their standards. And so I want to focus a little bit.
The standards versus guidelines. You'll notice that's what he's talking about.
On them, but also ISO. We go outside the U.S. We see ISO, the military for our military products, hazardous materials. I see we have a speaker coming up to focus on hazardous materials, governed by the Department of Transportation. And if you ship in the less than truckload, the LTL environment, then you're dealing with the NMFTA, the National Motor Freight Traffic Association. So ISTA. The International Safe Transit Association is a small organization based out of Michigan that is focused solely on publishing standards for the simulation of distribution environments. Okay, they will actually reference ASTM standards on how to set up equipment. Okay, they don't get into that. Their focus and the focus of the current efforts they have at characterizing distribution environments is for the purpose of generating and updating standards related to the simulation of particular environments. Okay, and we can talk a little bit more about that later. They also offer the opportunity to certify packages. So you take one of their tests and you take your packaged product, you go to a certified lab, you're a member of ISTA, your packaged product passes the test, and it enables you to put a transit tested stamp on your box saying.
So an advantage of that was when I worked at UPS, if packages were ISTA certified and they had damage, it was much easier for them to file a claim and get paid for it, because they could say the packaging was adequate for the standard distribution environment of a small parcel like FedEx or UPS. And if it got damaged, that meant that something extreme happened. The product was packaged for the environment. And if it got damaged, something must have happened. So it was much easier for people to get claims paid if they filed a damage claim and actually get compensated for their damage.
we've done the best we can to assure that our packaged product system is designed to survive this particular environment, okay? Maybe like signing the waiver form and acknowledge, when you go rafting, okay? It's we recognize that, that we're doing the best we can, okay? They have recently become an ANSYS consensus standard writing body. This might not be a big deal to us in this room, but it really is to the medical products industry, okay? And they have incorporated some of their standards recently to actually be consensus body standards, which is the next level of certification and is important for some people in this business of package testing. Another organization is ASTM International. Their focus is a massive organization publishing all kinds of standards for everything from amusement rides to how to.
And for packaging, we see it for transportation, but we'll also see it for material properties like tensile strength or compression strength, and those sorts of material standards for packaging and how those tests are done. Those are done through ASTM, or those standards come from ASTM.
For concrete. They also have a committee, the D10 committee, that is focused on packaging and package testing. And most of their standards in that D10 committee are related to the setup and the proper methods for conducting tests. They published 2 standards for the simulation of the distribution environment. And the kind of across the board big one is the D4169, which if you're in this even remotely, you're probably familiar with this particular test standard. It covers a lot of different packaged product distribution routes. There is another one, the D7386, that is focused just on the small parcel delivery system and the growth that we've had on that.
Which is FedEx, UPS, I guess Amazon now, but those are, like air shipments, truck shipments that go from one distribution center to the other versus, long haul full. And these are individual packs on a truck, mixed loads versus a full pallet load of the, pallet loads of the exact same thing or many pallets on a truck.
A lot of things just in the past 10 years. Okay, so depending on your packaged product configuration, we generally see a division in 2 different types of a breakdown, and we look at it 2 different ways of the types of test elements that your packaged product would undergo. And this probably makes sense to a lot of us in here. If you're shipping unit loads, then we've got larger, heavier things that we're handling mechanically that might be getting stacked in a warehouse that undergo shock events that are very different from the way we might handle a small 12-pound package, okay? So that unit load delivery system is going to involve hazards like atmospheric conditioning, rotational edge and flat drops, incline impact, vibration, compression. Whereas when we move to the small parcel delivery system, our smaller items that we're manually handling that are going through distribution centers and sorting operations and ramps and sorting arms and conveyors and all of these, we still are often concerned at the general simulation level with atmospheric conditioning. We look at, instead of rotational drops, rotational flat drops and edge drops, we would see free fall drops, okay, from.
So noticing that video I showed you with the drop tester, they were rotating that box and dropping it on corners and edges. That's going to be more in line of what you might see in an automotive environment versus the small parcel. You're going to see more hand carried parts or packs or things going on conveyors.
Handling of packaged products. And we would see vibration and compression often combined. And the reason we do this, these compressive forces that exist in the backs of our trucks, planes, and trains, where packaged products are stacked on top of each other and now are undergoing an acceleration event because they're moving, that dynamic compressive force we try to reproduce in the lab by testing our packaged product with some design top load. on top to simulate what could be placed on top of the packaged product based on densities of freight that these carriers often move. So I want to say a little bit about some of these primary test elements. The atmospheric conditioning. Fortunately for us in the lab and for you as people who have products you need to test, we don't have to bring our entire lab atmosphere up to 104 degrees Fahrenheit and 85% relative humidity. That would kill us in the lab. What all of these standards make provision for is the ability to precondition our samples for some period of time so that we can come to equilibrium with the moisture, available moisture in that atmosphere and temperature and our packaged product, okay? So that we can immediately bring that out of the chamber and go in and start testing. So often these preconditioning times are anywhere from 24 hours to 72 hours, depending on the test method, and oftentimes depending on the packaged product. Do we have a unit load that's wrapped in plastic and our interior product has a primary package that's also a polymer and various levels of corrugated? If so, we need more time to come to equilibrium, okay, in that example. A concern with this is some of these tests run for hours. Some of the vibration tests can be 3-4 hours long, and we're losing conditions. If we come out of a hot and humid and go into a lab atmosphere, we can begin to lose our conditioning. And so oftentimes there's even, it makes sense to go back into the chamber for a period of time to recondition before that big compression test at the end. So atmospheric conditioning, we see all the way down from frozen all the way up to tropical conditions.
Minnesota and Florida.
The small package product. I know it seems simple, but a device that can repeatably drop your packaged product in the same way every time. When we drop a flat, the spec says you want to drop flat, you got to drop within 2 degrees of flat. So that what we perform to packaged product A is the same thing we do to B, it's the same thing we do to C, to enable even comparison and enable us to make decisions. A lot of times we will even take those impacts that occur in the distribution systems that aren't manual, that these sorting arms and the slides where they impact other packaged products, we'll take those events and create an equivalent free fall drop event. So based on the velocities of that sorting arm that comes out and hits our packaged product, we can use that velocity to back out, this is how high we need to drop things from in the lab to simulate that mechanical handling event that happens in the distribution center. Okay, another is, and this is a common one, you say, well, wait, can't I just do this out in my shop floor? Yeah, you could. This is, I kind of loosely refer to these as the floor exercises of package testing. But if you look at them, they're practical, aren't they? Mechanical mishandling of unit loads, where a Ford truck driver catches the back end on a unit load behind it, goes to slide forks out and things rotate down and impact. We're looking for practical connection to application of some of these very simple tests, apparently, that we do in the lab. Not common in the distribution environment, but some of you might be dealing with standards that specify this, is a free fall drop to a unit load. I've not witnessed one of those. I hope that I never do, but yet we specify this as a test element, to which I would encourage you to consider introducing the use of a rotational flat drop and or rotational edge drop, as you saw.
So this is where he's talking about how, we have standards and guidelines. So the guidelines recommend probably, worst case, trying to look at what's typical in the environment for distribution. But he's saying, you really have to think about and understand your what your system looks like for your supply chain, your value chain, and all those things. You want to know what that distribution system looks like so you can simulate what's actually happening. How are the fork truck drivers handling it and so forth.
illustrated in the video, typically done to two adjacent corners of the device. So we're seeing both axes of the unit load and how they respond to the impact forces that transmit through our packaged products and you know, that are very possible and could occur in distribution. Okay, another common one for unit loads is this incline impact test. And I think it's important for us to think about first to discuss what it is not. What this is not is simulating rail car coupling. Okay, these rail cars with suspension draft gear, that when we couple these rail cars on the railroad, that could be 5, 6, 7, as high as 8-mile-an-hour impacts that occur. With rail cars that have suspension systems that are designed to withstand that. And so they take these short duration, high intensity accelerations, and they drag them out over a longer period of time. Now, the nice thing is for our packaged products, the peak acceleration drops, but it creates much lower frequency shock events than we see with the typical incline impact test. And we're going to talk a little bit more about the test that is done to simulate those in a few minutes. But the incline impact test, as you see it here, is specified based on an impact velocity. Okay, so we need to reproduce with our little sled up against the stationary backstop a particular impact velocity. Okay, let's say it's 4 miles an hour. And at that impact velocity, we're going to impact the packaged product on all 4 vertical faces of the unit load. And we're looking for, then we look at response of the products inside and shifting and ability of the packaging to contain things.
Now, notice he says they do it on all 4 sides. This is a pallet load of boxes that's stretch wrapped versus RC9 is talking about bins, the full bin, and even, you know, making sure if there's an access door on the side that face hits the sidewall or the backstop of the incline impact tester. So just to show you about ways that you look at what's actually happening and get a repeatable test to simulate what happens in whatever environment you're in.
Maintain unit load stability through a test like that. Where does this come from? Truck driver hits the brakes, deacceleration, backing up, hits the loading dock. The interaction of freight as we're cornering and braking and accelerating, deaccelerating is where we see these short duration, okay, high intensity shock events. And so this is a very common test element for unit load testing. Say that probably the single most popular thing we do in the lab is run vibration. It doesn't matter what kind of packaged product it is. If it comes through our lab, it's going to spend some kind of time on the vibration table. And that makes sense, doesn't it? Because all of us, it's the one input that all of our packaged products undergo. There's some type of transit that takes place, truck, plane, or train. We're in a vehicle that is receiving vibration. And so these modern vibration systems are capable of reproducing the nature of the motion that exists out in the environment that we call random vibration. This is vibration that occurs over a range of frequencies and at varying intensity levels all at the same time. It's a very complex motion. It's complicated to reproduce. We bring it into a lab and there's some trade-offs. When we do a vibration test, we are not simulating that truck going over potholes or railroad tracks or the speed bump or catching the curb as they go around the corner. Those discrete events get filtered out. What we're capturing is the over-the-road response of the vehicle to that rough road surface, okay, which we get exposed to for hours. So we're not seeing the discrete events, but there are profiles that exist for trucks, for planes, for aircraft that we can use and play on these vibration systems. As I mentioned a moment ago, that focus simulation, where companies will mount data recorders on their truck and they'll record 5, 10 different trips with that truck.
So you see, he talked here about the testing for the vibration table. They're trying to capture like a long-term road trip, but part of RC9, they're trying to capture some of the events. You know, we talked about that in chapter 3. So, you know, want to kind of balance out capturing shock events or filtering them out and looking at long-term fatigue.
And take that data and average it together and use that, and we can load that into our vibration system and reproduce your truck ride. A lot of these standards are taken from roads in North America. There's being work done globally, but to characterize roads and vehicles, but a lot of them are in North America. A lot of them are trips across the country that are instrumented and used for these general simulation profiles. How helpful is that to you when you're shipping product from Anderson to Greer? Maybe not so valuable. That's a 30-minute trip. And these tests are designed to simulate hours of transit, 10, 20, 30 hours of transit if we're going all the way down to Mexico. So if you're in that category of products from Anderson to Greer, maybe it's even more valuable for you to instrument your own vehicle and know what your vibration profile looks like and damage exposure could be.
Yeah, because if they're going on a 30-minute trip and it's a really bad road, or there's a lot of construction, or there are huge potholes, or there's some hazard that is causing shock events, capturing that profile means a lot more to them than if it's a brand new smooth road and there aren't that many events with the drivers versus doing a long road trip. So those are some of the things to look at.
Okay, another one is compression, compressive forces. And we see it being done here with a unit load product where in two ways to approach this. One, from a performance testing approach would be to say, hey, let's calculate what kind of compressive loads we could see in the distribution environment as we stack these things in a warehouse. We're going to stack these things 2, 3 high. We can calculate a load that will be applied to our unit on the bottom layer. Let's just apply and release, or apply and hold for an hour or for 3 hours, that load, and see how our packaged product responds to that. The other approach I would consider to be more the engineering approach that we include in the development phase is we're going to compress it until it fails. We want to know how much load our packaged product system together, where maybe our product can share in the load bearing, is what load that whole system is able to support.
That's more of what chapter 3 was talking about as far as test methodology.
Environmental conditioning, particularly when it comes to compressive forces or dynamic compressive forces and vibration, environmental conditioning becomes a very important step in the process. A lot of our materials, for a lot of us in here, we do a lot of returnables, largely made from polymers or steel racks. Temperature might be a bigger issue if we're dealing with polymers, but a lot of us for whom we are dealing with expendable packaging that involves paper-based, corrugated materials, moisture is significant, has a significant effect on the mechanical properties of these materials. And so it's important for us, in conjunction with compression, to know what environmental conditions that we're at equilibrium with. Often could be standard conditions, that's fine, 23 degrees Celsius, 50% relative humidity, but there might be interest in us testing at really high temperature, high humidity. It was nice out here this morning. A week ago, it's not so nice, it was hot and humid. And our packaged products go through this environment, and it has a big influence on our compression performance. So I just want to briefly hit on some other test elements, maybe that aren't as typical in some of the test methods that we use, but are available to you as you are constructing maybe your organization's custom design plan or test plan. There's a tip over test, fork truck handling course, horizontal impact, concentrated impact, and what's called a bridge impact. And I just want to show you briefly what these look like. Okay, the tip over or tip test, hopefully it's a tip test. If we get to the point where things are tipping over because our base is so small and our center of gravity is so high that we actually have the propensity to tip over, then what's recommended is a tip over test, where you find the balance point and push it past that and let it go and see what happens to your packaged products. The tip test is, let's take it to 22-degree tip and release it and see if it comes back, and is helpful in developing the footprint necessary to maintain stability of what could be a top load, a top heavy packaged product system. Another, and this is gaining in popularity. This is actually the photos I've shared with you here are directly from the ISTA, International State Transit Association's approach to fork truck handling course, as they specify in a couple of their standards. And it involves a course set up with some predetermined sized hazards that are placed along the floor, different heights and configurations, and you drive over the course with the packaged product at about a medium to slow walking speed, and then you back up, and that's one cycle. We do 4 of these cycles. We change orientations if it's a 4-way pallet, and we do another 4, okay? And we're looking for effect, obviously, on product, packaged products, that whole system's ability.
So again, this is not in chapter 3, but this goes along with the whole understanding what your true distribution environment is. And if you need to develop a repeatable test to figure out where damage either is occurring or could occur, then this would be an example of something like that. Standards are constantly being updated or changed depending on learnings.
To maintain unit load stability. I mentioned the rail car coupling, okay? And the fact that the incline impact test is not designed to simulate that impact. And largely because of the duration of the impact. To maintain that long duration could be 30 milliseconds, it could be 300 milliseconds. We need specialized equipment to do that because the impacts that occur with the incline impact tester are more on the order of 2 to 3 to 4, maybe 5 milliseconds. So these are a lot longer events. Intensity is lower, but because of that lower frequency input, that might match a fragility of our packaged product systems. And we might see, and these are horizontal loads, right? So we might see a loss of integrity of our whole unit load. We could pass the incline impact test, but we can't pass the horizontal impact.
So this means that something could get put on a truck and it would be fine. And, you know, even the stops and starts and turning of corners and those events for a truck driver, but you move this onto a rail car shipment and now all of a sudden you have damage. That is what you know, those are some things you want to look at, understanding the differences in the environment.
This equipment is expensive. There's limited labs that have this available, but there are some here, certainly in the Southeast, that up in North Carolina that have, and one in Georgia that have this kind of equipment. Okay, another is concentrated impact. Applies to our small things. We ship through, if you could imagine
skip over that. Like I said, you can watch this later if you want to. I think it's really, really interesting, but you know, I'm gonna probably wear my packaging nerd t-shirt next week, so you all can see that. But this is good, really good information.
Impact. This is again, this is going to be small parcel environment.
Again, small parcel versus larger returnable packs.
You can expect when you go through this lab testing is to get a really complete lab report. Or components.
And like I said, I've seen the reports. I worked with them on automotive packaging before, and the reports are really good.
I just want to leave you with a few best practices. I can't stress enough the importance of understanding your distribution environment. To understand all the steps that happen between that A and B and maybe C. To firsthand watch these things happen. There are a lot of things we take for granted that we think, hey, a truck took this away. Certainly this is being handled only by truck. But if your LTL carrier very possibly is taking that truck and bringing it right to a rail yard, because it is less expensive for them to move that product via rail car, and it ends up going through a handling system that places this on a rail car, on a flatbed rail car, and that spends a dominant amount of its time in transit on a train. We take for granted in the US that we handle pallet loads with fork trucks. We go outside the US and I've heard cases of where pallet loads are even handled manually. So there's not a fork truck available. And so
yeah, I've seen it where they load things box by box onto a sea container or a truck. And then when it gets to the final destination in the US, they have to unload it by hand because it was loaded by hand because they didn't have fork trucks on the supplier end.
There's nothing like seeing and understanding your distribution environment. I encourage people to overpackage to get things to the test lab. We don't want to include whatever happened getting your products to the test lab as part of the test.
I've seen that
So
happen.
either we're going to overpackage, or we're going to send people there and inspect them prior to the test, so that we know the condition of our packaging, the conditioning of our products.
And that was that when I showed that picture for FedEx, I was showing how you want to cushion around it. That's what he's talking about.
To starting our test. It's also very important to provide, to have clear damage criteria, both for your product, what constitutes damage and what doesn't, and for your packaging, what constitutes damage and what doesn't. The lack of clarity there on the part of organizations conducting these tests leads to results that really aren't helpful. So clarity up front on that is important. And I've mentioned.
So you might have a part that it might get scratched. It may not be important for it to be scratched, or it might get, or some things, they have functional tests where they turn it on. I have one of my clients where they have a part where it can turn on, but it could have some damage, so that you can't tell till you actually run it. So they don't just have to turn it on, they actually have to run it and see for a cycle. Is it actually working, or did it get broken?
It's already the importance of being there, seeing, hearing what it sounds like for your packaged product to undergo a vibration or a shock event. So with that, I'll leave you with an image of our last speaker. James was based out of CU ICAR.
Testing for double stacked pallets. And then
He's probably got some good questions on here.
but how does that impact? I mean, their way to put I don't know, change the criteria. In other words, vibration testing for double stacked pallets. And then that compared to rail versus truck versus sea versus air. You know, and then
She mentioned
if
ocean,
it's
he didn't mention
overhanging the
ocean.
pallet a little bit, how does that impact? I mean, their way to put in those different variances to understand what can happen. That's more real life, at least more in my real life.
Yeah, dealing with double stacked unit loads and loads that overhang the pallet or underhang, and the effects of that when you stack them. Absolutely. Okay. I would encourage you to test under those configurations, okay, with a caution, okay? A lot of these tests, and when it comes to vibration, since you mentioned vibration in particular, these vibration profiles are generated by recording a bunch of vehicles, averaging all this together. And then I mentioned the time compression. They will increase the intensity of that profile to decrease the test time. And that works. Maybe like you could cook your cake a little faster if you increase the temperature, okay? But if you increase it too much, you burn the cake and everything inside doesn't get cooked, okay? That same thing can happen in package testing, is that we burn the cake. And when we start to double stack, taking vibration profiles that are already time compressed, I have seen an over testing of the packaged products because of the amplification that occurs through that double stack. And typically, you know, our lower levels don't see as high a vibration level as we do at the top because of that amplification that occurs through the stack. And so I often see an over testing that occurs when we do double stack. So being sure to make sure you're using profiles that aren't significantly time compressed, okay? And those are available.
Sorry about that.
Oftentimes we see a lot of, I consider over packaging. In your lab report, do you ever see it pass, but actually could say for one-time use expendable packaging that you could actually downgrade the material for a cost savings or material savings?
Yeah, good question. So, you know, as a testing lab, you know, our job is to perform the test, give you the results, so that a lot of those decisions can be made, by you, okay, as the customer. However, when you come, and one of the benefits of being there in the test is you're conducting this test with technicians in the lab who see a lot of this stuff, and just in conversation we can comment to the, you know, off the record. Wow, we're overpackaged here. And to that point, we see a lot of that. We see a lot of overpackaged product. We don't know what kind of inputs these things are getting. We really don't know the fragility of our product. Let's just beef up the packaging. But then we're spending that, we're doing that overspend on every unit we ship out the door, right? So yeah,
That's true. People will overpack to make up for it, and they're spending a lot of money when all they have to do is spend a couple $1,000s to do testing and the right testing. So very good point.
there's definitely a lot of that we see, and an opportunity to comment, not officially so, in the form of a report. So good, thank you.
So you do a lot of testing for damages during transit point A to point B, like you said, as far as internal damage. Do you do any testing for any environmental factors such as corrosion or damages inside the packaging?
So things up 12,000 feet pressure. We're going to put something in an airplane. What's the effect? We're going to put something in a truck and drive it through the Eisenhower Tunnel on I-70 going through Colorado and get up to nearly 12,000 feet. Pressure changes, yes. Corrosion, there are test methods to do that. It's not something that we do in our lab. You know, beyond just putting something in an environment where we control temperature and humidity to some high level. And we have done that. You know, we've done even short, you know, I know a lot of our products in here are made of metals that for which they exhibit corrosion, and maybe we can't even put coatings on them. And we're exposing them to an environment over the course of just a few days where we can even begin to see some surface rust. That kind of testing, yes. But long-term salt sprays, months at a time, we're not set up well for that, but I'd be happy to direct you to some labs that can.
Those are more material testing.
There's probably other things
protocol.
we can think of. UV exposure. How about exposure to rain? We make the
For parts.
assumption that our packaged products stay under a roof all the time, but even that might be a loose, loose assumption to make. So, thank you.
Good morning. Is there an ASTM standard for a preload on a compression test?
Preload on a compression test. Yes. So let's think about.
So I'll skip over that, but as you can see, Dr. Batt is brilliant. He does a
Based
lot
on the
with
number of
testing.
walls of corrugated board in the container, and it's that simple.
So I'm going to stop there. Again, you know, great. If you're go back to, you know, when you get into 410, if you haven't already taken it, he gives some really good points about how to, you know, how you're packaging and he's relating it to automotive. He's comparing automotive to some other things. So some other types of packaging. Brandon, if you're still awake, I would love to hear your feedback.
Yeah, it was definitely a great presentation. I feel like this one and then the last one that we watched about was going over the different, you know, graphs and sine waves are great because it gives that background information. So you're no longer just relying on the data that these machines give you. So it's like I can actually understand a few of these things, and especially with the questions he was answering at the end, is like even with experience with the machines, you still find yourself asking these if you don't know the background. So definitely like that. So I was looking forward to 410 so I can finally understand a lot of those testing procedures.
Yeah, there's a lot more out there now. When I took the equivalent of 410, we didn't have the luxury of YouTube. So, you know, we had to get in the lab and we did a lot of calculations and we dusted off the calculus and all that good stuff. So, you know, we had to like chart stuff out and do the formulas. Now, the computers and the systems do a lot of that, but it's really, really important that you understand. It's really important that you understand how these tests were derived and what that data looks like and why they chose the test and, you know, that they're using. Specifically for automotive, because, you know, like he mentioned about using returnables, because the way the polymers perform is different than a corrugated box. So, you know, the test that you choose can be different or will be different. And whereas corrugated boxes, they're going to show more fatigue and failure in Florida in the summer, but a plastic returnable is probably going to show more failure in Minnesota in the wintertime. So, those are just some examples of how important it is to understand the environment, the packaging, the product, and all together, the distribution cycle, what it looks like. So that's what I have today. Like I said, I was gonna go over some of the homework. I think we're pretty much at time, but I did want to run through. Let me stop sharing on my screen for a minute. Get out of this. Let's see. I had a couple of questions I wanted to go over really quickly, but I'm hoping that some of this answers some of the homework questions. And Brandon, did you have any homework questions? Because what I'm finding is everyone seems to have the same questions.
Not yet. Only on number 5. So still got some time.
Okay. All right. Great. Let me pull up the first question that I had, which was, let's see. I think I've gotten a lot of emails since we've been talking. Much of it is junk mail. Okay, so first one was number 4. Let's see. Number 4, the question was looking at trying to locate the weight that's being used in RC9, test number 9. So for this one, for question number 4, this is the one where I said you need to go look at the information from the manufacturer. So, this is the one where I said to go Google the manufacturer, which I think was Rollpack, and look to see what the capacity is that's listed for that particular supplier of the packaging. See, okay, so number 1 was the question about, what would happen if you changed out the truck and the weight for and I'll just read the full question. That's probably easier for that one. So number 1, the question is, if you ship lightweight sheet metal parts in rail cars that are designed for heavy loads, the parts rattle and bang into each other. So again, let's say you have this and it's a it's a rail car made for heavy loads, which means it has a heavy suspension, and the parts will move around quite a bit. So the question is, if you ship heavy parts in a rail car designed for lightweight parts, what would happen to the parts? And I said, think about a golf cart that is designed for holding 2 people, maybe your golf clubs, and that's it, on a grass trail. But now you want to load this golf cart with, like 5 grown football player men, and you're going to put, heavier bowling balls in the back. Maybe put 10 bowling balls in the back instead of a couple of golf bags. What would that golf cart do? Because that's really the equivalent of having a rail car. In this scenario, you can look at it, a rail car that's designed for lightweight parts, but you put heavy parts in it. And it's not designed for heavy parts, it's designed for lightweight parts. So, just think of that, what might happen. Let's see, number 6, the question was, in RC9, tests done on individual totes, why do they use a 40-pound test media? But for the large bins, the test load is based on EFW. So for that one, you need to look at, just one second, pulling this question up here. Okay, so for number 6, you're looking at, you know, what is driving that weight for the bins? Because I'm sorry, for the handheld totes, the bins, you're moving around with a fork truck, so you're not really focused on the weight of, you know, what's in there. There's not necessarily a limitation, or the limitation is higher than what you'd handle with a fork truck and what that bin could handle. Versus a handheld tote, what is causing you to determine a weight for a handheld tote? What drives that? And even if a handheld tote you could actually hold 500 pounds in this small handheld tote, but you're not going to test it for what it can hold because it's a handheld tote. What determines that weight limit? Why is it limited to 40 pounds? So I think those were the questions that I had from homework. So I hope that helps to answer the questions for anybody that's looking at it. I found that people tend to ask for help for the same questions. So let me know again if you have any questions. Join for office hours tomorrow. Email me, whatever you wish. But can't wait to see your homework. All right. Anything else that you can think of, Brandon? Any questions before we sign off?
Nope, I'm all good.
Okay, great. Well, thanks for attending, and I hope you all enjoy this lecture, and I will look forward to your homework. Hopefully see some of you on office hours, and I will see you for the next lecture next week. Thank you.
All right, see ya.